Yeah, and thank you, Flora, and thanks to all the organizers for the invitation to speak. So I have to begin this talk with a bit of a disclaimer that this might be a bit of an outside perspective, and that I'm not a seismologist or don't work in earthquake engineering or hazard assessment or things that we've been hearing about today. But in general, I work on computational tools for uncertainty quantification and tools that will really live at the intersection of modeling and data. And so I hope some of those might be relevant today. So in this talk, I want to talk about inverse problems, which are really a building block for how we answer so many fundamental questions. Essentially, how do you integrate models with data? How do you learn a cause from an indirect effect? In other words, how do you surmise what's happening given the observations that you have and models that you might have in hand that describe how those observations might arise and how they depend on the physical things that you care about. Now, to make that a bit less abstract, these are questions that, of course, cut across a very broad spectrum of fields, ranging from scientific inversion to health monitoring, and also things that are quite far away, whether it's geophysical remote sensing, chemical kinetics, so on and so forth. And inverse problems also come in sort of many almost synonymous phrases: data assimilation, history matching if you're an oil person, model calibration from a statistical perspective, plain old parameter estimation, signal recovery from a signal processing perspective. All of these are in general inverse problems. And so I want to talk about computational methods for inverse problems, and in particular, how to assess uncertainty in the solution of inverse problems. Now, just to give you kind of one quick example, this is some work that I did with Ruben Juanes and company at MIT, where essentially here are the indirect observations were things like ground deformation, maybe pressure in some wells, and we wanted to then learn aquifer properties and fault properties from those observations during an injection event, during a CO2 injection process, and looking at the seismicity that they introduced. So in some sense, we're trying to learn, in this case, model parameters given rather indirect observations. And the models essentially mediate between the parameters you care about that describe the subsurface, describe the fault in particular, and the things that you can actually observe. And this is a very interesting kind of coupled flow and geomechanical model. The model itself was quite elaborate and quite expensive to evaluate. And some of the methods that I'm going to talk about for the next few minutes are essentially essential to making inverse problems in this kind of setting tractable. So, okay, some common characteristics of inverse problems, kind of coming back to the large scale. We're looking at problems where observations are indirectly related to the parameters. The observations might be limited in number, but I say, or maybe not. Maybe you're looking at waveforms, which are in some sense high dimensional data. Observations are typically noisy, and the parameters are often, but not always, high dimensional. Now, these are kind of the things that are, not every inverse problem exhibits all of these characteristics, but these are common attributes, and these are things that might make your inverse problem challenging to solve. So, okay, in this talk, I want to discuss broadly a statistical perspective. It's actually going to be a Bayesian statistical perspective of inverse problems, and we've seen a lot of statistical perspectives in talks already, so I'm probably preaching to the choir here. But the usefulness of this perspective is really to characterize uncertainty in the inverse solution, to understand how it depends on how many observations you have, how rich your data is, features of the forward model, what kind of prior information you might bring to the table. Also to design useful observations, to assess the quality of a sensor network, you need some notion of the uncertainty that comes from this sort of candidate sensor network or the network that you have. And if you want to make it better, if you want to do something like optimal experimental design, you need to carry around a measure of uncertainty. And then we want to make take those uncertainties, push them forward to predictions. We'd like to do things like guiding decision-making and optimal design under uncertainty. And also the last question, maybe the most difficult question, is we want to be able to assess uncertainty as a way of trying to address these questions of model misspecification, model validity. The models we're going to use are inevitably approximate, inevitably wrong in some way. How can we characterize that uncertainty in all of the decisions and conclusions that we make above? Okay, so that's kind of a tall order, but to begin with, we're going to sort of start addressing this problem by taking a Bayesian statistical perspective. So again, this might be quite familiar. I'm preaching to the choir, so just maybe we'll use this to set notation. Essentially, I'm going to use X to denote model parameters, Y to denote observations, and the Bayesian approach. Okay, you might say that the interesting thing about it is Bayes' rule. I contend Bayes' rule is kind of a tautology. It's not terribly interesting. What's interesting about the Bayesian approach is that you're using probability to represent your state of knowledge about parameters. So the model parameters X are treated as random variables. That's really the distinguishing feature of the Bayesian approach. And here we're just going to kind of have a simple setting. It's not a hierarchical model. This is kind of a one-level Bayesian inference. You could certainly make this much more elaborate. but X are model parameters, Y are the data. I'm assuming everything has a probability density. There's really two interesting objects on the left, on the right. There's the prior probability density. So it's things you know about the parameters before you see the data. The likelihood, this is really where the forward model, where the physical model often lives, or the thing that relates your parameters to your observations. It's P of Y given X. And that's represented by this blue figure here. And then the product of those things is proportional to the posterior probability density, which is essentially your posterior state of knowledge about the parameters, having observed these data Y. And that's essentially the essence of Bayes' rule. You could really think about this as updating your prior state of knowledge into a posterior state of knowledge based on a finite set of observations that you might have and that you might be able to explain through this likelihood function. And I'll get back to this later, where essentially the role of the likelihood function is to explain the observations probabilistically. It's statistical modeling meets physical modeling, and both of those are really important in yielding kind of honest or true or kind of representative uncertainty quantification. Okay, so that's kind of the basic setup, but the challenges that follow from just writing down Bayes' rule are generally computational. We need to characterize this posterior distribution. Typically, that means we want to draw samples from it. And this could be challenging because the parameters might be very high dimensional. And also, as we've seen in previous talks, the models that we need to use, for instance, to evaluate the likelihood function might be very expensive. They might be simulations on supercomputers in and of themselves for one candidate value of the parameters. And so just as a typical example, you might say your observations are predicted by some deterministic model f of x, where I plug in the parameters x, perturbed with an additive Gaussian noise whose covariance is sigma. And this means every single time I go and evaluate my likelihood function, I need to go evaluate this expensive model f, and that could cost me a lot if I just take sort of a naive brute force approach. So these are the computational challenges. And then the last challenge I want to talk about is, okay, so you go through all the trouble, you characterize your posterior, you essentially have samples from which you can then assess quantiles and risk. You can take integrals over tails, you can take means and covariances and standard deviations, anything you want. But in what sense do those really capture the uncertainties that you care about? So these are computational questions, and this is kind of a modeling question. Now, any one of these could be many talks unto themselves. So what I want to do for the next 10 minutes is just kind of give a glimpse of certain underlying challenges and a few attempts at addressing them. I want to talk about how to deal with the high dimensionality parameters and data, how to deal with computationally intensive forward models, something actually previous talks have talked about as well. And then the last, maybe squishiest, but I think most important topic is achieving honest uncertainty quantification. So I just want to walk through these things, and this will be at a relatively high level, but if you have detailed questions, of course, please put them in the chat. So first, high dimensionality. I'll begin with an empirical observation, which is that in many inverse problems, the data only inform low dimensional subspace of the parameters. So in other words, if you think your parameters live in RD, there might be a subspace where the posterior and the prior are very different from each other, and a complementary subspace where the posterior and the prior are generally quite the same. In other words, like if this is sort of in the cartoon of my prior knowledge, some isotropic Gaussian, maybe the data are really only informative in this direction. They're really only updating my belief in this direction and not so much in this direction. Now, this structure actually shows up surprisingly often, and it's really due to the kind of intrinsic ill-posedness of inverse problems. The fact that your inverse problem is ill-posed, that people in the deterministic world think about all kinds of regularization schemes, is really part and parcel of this observation, which is that the data may not observe, for instance, fine scale, may not inform fine scales. If your data are over here, then maybe they're not so informative about parameters that are far away. Some parameters matter to the data and some parameters not. And this structure is something you can actually exploit computationally. If it's a linear Gaussian problem, it's something that we sort of now have a pretty good understanding of. And in the non-Gaussian case, we don't necessarily have optimal approximations, but we have nice approximations with certified error bounds. I'll just give you a sense of what these things look like. You can really think about this as all stemming from low rank of the Hessian of the negative log likelihood. And in many inverse problems, this data misfit Hessian, you could call it, has a compact or rapidly decaying spectrum due to few observations, due to smoothing character of the forward operator. This happens if I'm observing pressure and trying to learn permeability. Then fine scales of permeability have very little impact on pressure, a lot of things like that. But there's also prior knowledge. Prior knowledge is part of the picture. And in general, if you have a Gaussian prior, the answer really lies in looking at this generalized eigenproblem, where this is the Hessian of the data misfit, and this is the inverse of the prior covariance, or the prior precision. This really captures the intrinsic dimensionality of the problem of the linear Gaussian case, and a very similar object captures the intrinsic dimensionality of the problem in the nonlinear, non-Gaussian case. So here's just a quick example from computerized tomography, where you're essentially trying to image a body here. We have sources of X-rays, we have detectors over here, and you could have sort of this limited angle observation where you have a few sources, and you can have a very detailed full angle observation where you have a lot of sources and detectors everywhere. And this is actually motivated by some project we did with a logging company, where they want to basically take quick snapshots of logs entering the sawmill. But you could think about this as any kind of imaging or remote sensing application. And here what you see is, if you just focus on this middle figure here, if you look at these generalized eigenvalues, in the limited angle case, these eigenvalues decay rather quickly. In the full angle case, there's more information in the data, the eigenvalues decay more slowly. And if you look at sort of the rank of the update, if you truncate the update in some way, the error that you make when you essentially restrict your attention to an optimal set of directions decays rather quickly when you have less information, and decays somewhat more slowly when you have more information. In other words, if you have more information in the data, you ought to be able to do more work. You ought to have to do more work. That's sort of maybe morally true. And that's what these approximations essentially give you. And the other thing that this gives you is a sense of how to compress the data optimally. Because if only a low dimensional subspace of the parameters are informed, typically there is a corresponding low dimensional subspace of the observations that also is maximally informative for the data. And this lets you essentially, find a low rank matrix that you can apply to the data Y to get an approximation of the posterior mean, of sort of a point estimate of the true parameters. You can compute this thing offline, and if you want to then do fast real-time reconstructions, this can be useful. And these are images of what happens in the cross-section of that log. This is using all the data. This is using certain projections of the data, and you can see with good enough projection, you can do just as well. The other thing I want to note, and I'm skipping mathematical details, obviously, but the other thing I want to note is that very often the parameters are not the thing you ultimately care about. That dimension reduction in an inverse problem ought to be goal-oriented. There's some real ultimate prediction goal, let's call it Z, that is some function of the parameters X. And that's important because there might be directions in the parameter space that are very much informed by the data, but that are essentially unimportant to the thing that you really care about predicting. And in that setting, further dimension reduction is possible because you really need to look at directions in the parameter space that are allowed to vary according to the prior and informed by the data, and simultaneously important to the quantity of interest. And so this sort of is a finer sieve. There's two needles you need to thread, and that gives you more dimension reduction. And this is an example here where essentially, you could think of this as a heat transfer example, where we're trying to learn the heat flux through this line here. If you have observations here, if you use a naive approximation, well, the temperature everywhere in the surface is informed about the observations, but if you really care only about the heat flux through the surface here, then only a small number of modes of the parameter space are actually both informed and relevant. And this optimal approximation then gives you a very nice decay of error with the rank of the update. So if you include the goal of your dimension reduction strategy in these kinds of approximations, and the error can decay quite quickly as a function of the effective dimension, versus if you don't include the goal, then you get this green and blue dashed line here. Okay. So essentially what these things amount to is coming up with optimal low rank updates of your prior knowledge. And you could think of these as approximations of common gain in the linear Gaussian case, but more generally, these are optimal low rank updates, optimal updates of prior knowledge along certain directions. And you can derive these directions explicitly in a whole range of interesting inverse problems. Okay, so that's sort of one piece. That's high dimensionality, one possible way of dealing with it. Certain classes of problems fall into this thing nicely. The next thing I want to talk about, and this came up earlier, is the construction of surrogate models. So we've already seen that when you're dealing with inference with very computationally expensive models, when you need these models to simulate the data and thus assess model data misfit, then surrogates are very important. And a very natural thing is to say, well, okay, let me construct an approximation of the forward model or the likelihood function over the prior. If I have some prior state of knowledge that says the parameters could be anywhere in this wide domain, then let me build a surrogate that's accurate everywhere. And that's a reasonable thing to do when it works. However, it's a bit wasteful because the data might actually say, well, if after the inference process you were done, you might learn that the parameters actually just lived somewhere inside of these green contours over here. And so you wasted a lot of effort building a surrogate model that's accurate over the entire prior. But there's a bit of a chicken and egg, because how did you know that the parameters lived here until you built a surrogate and did inference and drew samples and did the whole thing? So this has motivated a lot of kind of interesting algorithms that are iterative that try to construct posterior focused surrogates. And this has been going on for a while. People have thought about polynomial approximations, data-driven model reduction, nowadays using sort of deep learning to essentially construct accurate surrogates over certain chosen regions.
Looks like
Marzouk, we lost.
Yeah. We'll just give a minute to see if the connection comes back.
If you can please send us a message in the chat so that we know if there is a connection issue or something.
Hello?
He's back.
Yes, you're
Hello,
back.
Yeah, my Zoom just died. So I apologize for that. Let me quickly get back up to.
Okay.